Hey, welcome to The Explainer. Today we're diving into something we do every single day but probably don't think twice about: measurement. The story of how we all agree on something as simple as how long something is, well, it's actually a pretty cool journey. It takes us from just guessing with our hands to building a global system that lets us describe a whole world in motion.
So let's start with a simple question. How long is this table? Seems easy, right? But the answer, it really depends on how you measure it. So let's join a group of friends, Deepa, Anish, Padma, Tasneem, and Hardeep, who tried to answer this exact question about a table in their classroom. And the tool they used? Their own two hands, the handspan.
So, what happened when they all measured it? Well, it was kind of all over the place. Padma got 13 handspans, Hardeep got 14, Anish was a little more than 13, and Tasneem was a little less. They're all measuring the exact same table, but nobody's getting the same number. So what is going on here?
Hardeep's the one who finally asked the big question: why should the number be different? And you know what? Tasneem figured it out almost instantly. The problem wasn't the table, it was their measuring tool. Their hands. They're all different sizes. If you have a smaller hand, you're going to need more handspans to cover the distance. If you have a bigger hand, you'll need fewer.
And right there, that's what we can call the handspan dilemma. I mean, sure, using your body parts to measure is super convenient, but it's totally unreliable if you need someone else to get the same result you did. It's a recipe for confusion.
You see, it really boils down to this. We need order, not chaos. Personal units like a handspan or a foot length or an arm length, they're just inconsistent. What we're really after is a universal system, something that's consistent and reliable, where a measurement means the exact same thing, whether you're in Mumbai or Mexico City or even on Mars.
And this hunt for order, it's not new. Not at all. In ancient India, they used units like the angula, basically a finger's width, to help design whole cities. Archaeologists have even dug up these incredibly precise ruled scales from the Harappan civilization. So yeah, figuring this out has always been a huge deal for any organized society.
And all of this searching led to a really powerful, game-changing idea: the standard unit. This is it. This is the official solution to the handspan dilemma. It's a unit that's defined so precisely that it just doesn't change no matter who is doing the measuring. It is the absolute foundation of modern science, engineering, and all global trade.
Okay, so how do you actually do that? How do you create a standard unit that works for the entire world? Well, you need everyone to get on the same page with a single shared system.
To get rid of all the confusion with different countries using different systems, the world basically came together and agreed on one system for everybody. It's called the International System of Units, or you'll usually just hear it called SI units. And honestly, this was a massive moment for global cooperation.
For length, the SI unit is the meter. And what makes it so useful is how it scales up and down. For huge distances, like between cities, we use the kilometer. That's just 1,000 meters. For everyday stuff, the meter or the centimeter is perfect. And for really tiny, precise things, we've got the millimeter. It's all clean, simple, and based on tens.
Of course, having a standard ruler is only half the story. You've got to use it correctly. You always want to place your scale flat against the object. And to avoid what's called parallax error, make sure you're looking straight down at the mark, not from an angle. Oh, and here's a pro tip. If the end of your ruler is broken and you can't see the 0 mark, no problem. Just start at the 1 centimeter mark, and whatever you measure, just remember to subtract 1 at the end.
All right, so we've got straight lines down. But what happens when you run into a curve, like the arch of a bridge or maybe the trunk of a tree? A stiff ruler is not going to work. The solution is actually pretty simple. Just use something flexible. A measuring tape is perfect, but even a piece of thread will do. You just trace the curve with the thread, then straighten it out and measure the thread with your ruler. Easy.
Now let's push this idea a little further. Measurement isn't just about answering how big something is. It's also absolutely essential for answering the question, where is it? This is where we shift from just measuring length to describing location.
So our friends are back at it. This time, they're arguing about what's closer, the garden or the school. Tasneem and Padma are totally sure it's the garden, but Deepa and Anish are positive it's the school. And here's the crazy part.
They're all correct. How? Because each of them is measuring the distance from their own house.
The key to solving their argument is this idea of a reference point. A reference point is just a fixed, agreed-upon spot that everyone measures from. If the friends had all measured the distance from, say, the main bus stand, then they would have all agreed on which one was closer. A reference point gives your location context. Without it, a distance is kind of meaningless.
You've totally seen this in real life. Imagine Padma is on a bus, and she sees a highway sign that says Delhi 70 kilometers. That number, 70, only makes sense because of its reference point, Delhi. The sign is telling her she is 70 kilometers away from Delhi. So when the next sign says 60 kilometers, she knows her position has changed relative to that one fixed point.
And that idea, that change in position relative to a reference point, that's everything. We've just built all the tools we need to start talking about the final and biggest idea, the language of motion itself.
So what is motion, really? It's just this. An object's position changes over time with respect to a reference point. You absolutely must have a reference point to know if something's moving. Think about it. When you're on a moving bus, the person sitting next to you looks perfectly still. But compared to a tree on the side of the road, you are both definitely in motion.
Okay, now that we can actually define motion, we can start sorting it into different types. The most basic one? Linear motion. This is just movement in a straight line. Think of a car driving down a perfectly straight road, or a soldier marching in a parade.
Next up, we have circular motion. This is pretty much what it sounds like, any movement that follows a circular path. The classic example is a merry-go-round. You're constantly changing your direction, but you always stay the same distance from the center point.
And our third main type is oscillatory motion. This one's all about that repetitive, back-and-forth movement around a fixed central position. A kid on a swing is the perfect example. So is the pendulum on a grandfather clock, or even a guitar string after you pluck it.
And just like that, you've got it. Linear, circular, and oscillatory. With just those three concepts, you now have the basic vocabulary, the basic language to describe almost any kind of movement you see out in the world. So where does this all come together in a really cool way? Think about a roller coaster. Those big straight drops, that's linear motion. The tight loops it goes through, that's circular motion. And the feeling of going up and down over the hills, that's oscillatory motion. We went all the way from a confusing handspan to being able to describe this complex, amazing machine. You have the language now. So my question to you is, what will you measure first?